So, from from what I learned yesterday, I went home and reviewed what I already knew and what I learned yesterday about how the velocity and energy are used to propel, theoretically, to keep the person in the same spot so you can cross the gap. But what I realized is that it's not possible to do that. The ball, so here's my explanation, is that the reason it's impossible is because the ball cannot keep the same amount of energy pressed up against the person for longer than the person, any amount of time after the person has touched the ball. It immediately loses that energy and starts to fall. So the ball would either have enough velocity to push the person upwards while he was moving forwards, or it would drop out from underneath him. But because the ball has no way of exerting energy by itself, it wouldn't be able to stay in the same position as the person crossed over it. It would have to move somewhere. So, if my tables are here and here, and the ball bounces up here, as soon as the person touches it, it will either push the person up or it will have to fall back down. And because it can't float here, it has no way of maintaining the energy to stay right at that height. And for that reason, it is impossible to cross between two tables by using a bouncing ball, not while maintaining the same height.
Oh, okay, I see. So anybody wants to comment or ask a question?
It looks like you made a restriction to where you can't go up or down a height, right? You just have to stay the same height as the
Yeah.
tables and use it as a stepping stone, right?
Yeah.
But you also don't throw the ball, are you? You're dropping the ball. And then if you're dropping the ball, then it goes up to the same height, and then when you are one step on it, it has zero velocity, so it has zero energy.
I don't think necessarily he's just dropping it, because the way his graphs are working, you could have either dropped it or thrown it.
The ball is being dropped from a height above where the person is standing. So it'll bounce.
So why can't you step on it and sort of feel it? Don't you put the leg out, or you will hit the foot of your foot from below, your sole of your shoe.
Right.
You will feel it.
Yeah.
That's the energy.
You'll feel it, but either it will push your foot up,
Yeah.
or your foot will push it down. But it won't stay there.
Well, it depends on the energy. What if it's a bullet?
I think he's meaning it'll be equal instantaneously, but after that one instant, it won't have enough energy to stay down, or you won't have enough energy.
Well, for the second one, I'm not sure. For the second one bounce, that might be problematic, obviously, because I just don't know. Even though if the ball goes down, so it gains energy again, it will at least it will go to the same height as it is right now. It will come back right to the same height. Whether or not I can actually use it again, they're unclear. But it seems that because it will come back maybe with zero speed, possibly. But for one step, I don't see why you cannot make one step and if it is going really fast or it is really heavy, why can't you at least use it for some support, so that you know?
Well, you can use it for some support, but it would push you up.
Well, that's what
But you wouldn't be able to cross it flat.
I'm fine. If I'm going up, I'm fine. Oh, that certainly is a good point. That if you're going up, it's even better. Yeah, now I see what you're saying is that it is very hard to throw it just the right way so that you would stay on the same level. Either it will be too fast or too slow. You will need an exact throw at exact speed that would provide you with support so that it reach the height, that height is exactly the same velocity that you need in order for you to step and not fall back down or be pushed up. So yeah, so in that sense, that is the very or impossible computation to carry out so that you would stay exactly on the same level. But the support appears to be there. Something that will help you either not to fall as fast, or even if it goes fast, it will actually push you up.
Yeah.
It's not a push. You see that the language is obviously incomplete. The story is about collisions. So like two billiard balls hit each other, and their collision is instant, and they exchange energy and they go back simultaneously. So you can think about two balls going up and down, and they both bounce off each other, right? So all of these are real possibilities.
See, here
Yeah.
I have the energy, which is what we figured yesterday.
Yeah, the graph one, right?
Yeah. And if we change this to the same weight as our runner, these would be our energy levels over time, with at 2 seconds is where the ball bounces. So it has the same, approximately the same energy here between these two. And over here I ran calculations of when our person, so this is the energy that he would gain as he went downwards, as he fell. So as long as the energy for the runner falling is less than the energy of the ball moving upwards, it'll push him up. So the ball doesn't...
So hold on, are you talking about the person falling down, in a way?
Kind
well,
of.
That's the energy, that certainly makes sense to me. So the person falling down is pretty much how much energy he might have throwing himself down. So if he cannot have more energy, then I guess that you can make a case that you cannot have more energy than that. So you cannot gain more energy than that as much as it is in your body, in both the body and the height. That's how much energy you have. And it might not be enough to give you support.
Right.
So I'm not sure that the second table on the next page. So you were looking at, get to blow it up a little. Okay, time. So weight. Okay, the weight of the runner, and so you look at the height, and you're imagining the person falling down.
Well, this would be his height as he steps off the table if the ball is not.
So height is two.
Yes,
2 feet high, and okay, that's fine. Okay, and then velocity is 0. It increases. Velocity decreasing. Okay, so and then so when you hit the highest velocity, then 291. Why didn't it go beyond that, or is it when you hit the bottom? No,
that's just where I ended it. That's what I took, because that's...
You don't have any energy when you are falling unless you're jumping. I don't even know if it's possible, but if you were falling off that ledge, at that point you have no energy.
Right. That's where it is at 0. 0 on this time.
So why don't you continue on when we see how much energy the person has when he hits the ground? Because you end at 1, at height 1. That's where you reach. Unless at 1 that's where you want to meet your ball. So, but you see what we're talking about. We're talking about the energy of the person falling versus the energy of the ball rising.
Yes.
That's exactly what the problem is about. So in order to because these energy are exchanged, and then based on that exchange of energy or the momentum, that their velocity then are determined. So are the numbers are so incomparable, or if the ball is obviously very light and the person is way heavier, so then give the person any kind of energy from the ball, which would have to go really fast. I wonder that the question would be how fast. You have to throw the ball in order to produce enough energy to support a person. So to give the person this much energy. So at 1, your energy is is what you have in the other table, and that's how much energy you're going to need in order to reverse that fall.
Yeah.
And that's what support is. So you start from 2 feet up, at feet 1 down, up, you need the ball going up, and then you compare energies, and then it's, so show me the numbers again. So the energy is 291. It doesn't seem that, well, why don't the...
I changed the weight of the ball to 180 pounds.
in the second table?
In this table, I changed the weight of the
okay,
ball.
so realistically, how much the ball will weigh?
I mean,
A pound maybe? So, so as you can see, the energy is
Very low.
insufficient.
Yeah.
I feel like it'd be on fire and it'd shoot through your shoe.
I mean, yeah, it would probably injure you
Yeah, that's,
by that point.
yeah, you
I
don't
mean,
want to hit this hard, so.
let's not go into that, because that would be like the size of the ball and
That'd be surface.
like surface area of your foot.
Yeah,
Onto the ball, and that just becomes...
yeah.
And then
it
that's
is okay from
that's-
this point of view. Imagine that you yourself is a ball, and the ball is a ball, and then they collide in a perfectly rigid way. So like two cannonballs hitting each other, and then it's like in a way like hitting with a bullet, you're hitting another bullet, and what happens to that bullet? So if they are two identical bullets, yes, but when you're trying to shoot down, for example, missile, right? So then the weight of your missile is probably smaller than the other one. If you were some kind of serious missile, surface-to-air missile, for example, and you have, that's what you have, and that one may be an intercontinental missile, and then so the weight-wise, you might have a big disadvantage. Well, so just to connect this kind of finding problems with a problem that has something more or less realistic. Okay, so we are out of time. Okay, so to just push the stop button there.